Okay, good evening once again. Today's lesson is going to be on empirical formula and molecular formula. And after that, we'll talk about concentration and also talk about percentage yield. But the bulk of what we are going to do would be with respect to empirical and molecular formula. Let me quickly add that this topic will be repeated in grade 11, so it shows you that it's important. There are questions in grade 10 based on this subtopic, and there are also questions in grade 11 based on this subtopic. So it will do you a great deal of good to listen and listen attentively. The interesting thing about this is that they are just calculations and they are straightforward. If you understand the pattern, there isn't much difficulty. So it's something that you should rejoice. And another thing I should add is that usually calculations involving empirical formula and molecular formula would attract, let's say, 5 or 6 marks. So even without having to do any proper revision, you'll be able to answer questions on that. Okay, so we'll go straight to the point. Now, what is empirical formula? The empirical formula or an empirical formula is defined as the simplest whole number ratio of atoms in a compound. And then we have another concept called molecular formula, and molecular formula is the actual. So you can see that the definitions are similar, except that this one is simplest and this one is actual. That is the difference between them. So empirical formula is the simplest whole number ratio of atoms in the molecule or in a compound, and molecular formula is the actual number of atoms in a compound. Now, for some formula, for some compounds, the empirical formula is exactly equal to the molecular formula. So, for example, if you take sodium chloride, this is the formula of sodium chloride. Sodium chloride as empirical formula, sodium chloride as molecular formula. In other words, you can't simplify it. You cannot make it simpler than this. Let me just give you a hint about this whole concept of empirical formula and molecular formula, and then you see what we are really talking about so that you don't get confused. In the lower grades, I don't know which grade, but your teacher must have taught you about expressions in mathematics, simplifying expressions. So if I write something like, if I write something like 2a plus 4b, and I say simplify it, all you do is to divide through by 2. So you divide this one by 2 and divide this one by 2. This one becomes a plus 2b. So you can't simplify this beyond this. This is the simplest form in which this one can exist. However, so in terms of if we're relating this to molecular formula and empirical formula, we'll call this the empirical formula. It's the simplest formula. Then the molecular formula is something like this. So basically, that is what I'm talking about. The molecular formula is either the same as the empirical formula or larger in terms of uh, the whole molar mass thing. Now let's look at this. So with respect to this, empirical formula is sodium chloride is the same thing. You can't simplify this beyond that. When you take that one for water, you look at it, it's the same thing. Water is like that. So this is what happens for some compounds. However, for most compounds, the empirical formula is different from the molecular formula. So we take an example of benzene. In benzene, we have C6H6. You can simplify this by dividing through by 6. So if you divide here by 6 and divide here by 6, you're going to have CH or C1H1. We don't write the ones there. So CH. So this becomes the empirical formula. We also look at an example of glucose. You have C6H12O6. Again, you can simplify this by dividing through by 6. If you divide here by 6, you get 1. You divide here by 6, you get 2. And then if you divide here by 6, you get 1. So it's C1H2O1. So this becomes the empirical formula. So basically, that is that. The last thing I want to talk about with respect to empirical formula and molecular formula is that there are certain compounds, especially when you get to grade 12, that have the same empirical formula, but their molecular formulas are different. So, for example, we have these compounds there. This is called ethene. This is called propene. This is called butene. So let's take the first one. If you have C2H4, you divide this by 2, you divide this by 2. This one and this one cancel, this one. So eventually you're going to have C1H2. We don't write the 1 there. So you see that the empirical formula is the same, but the compound is different from this one. This is C3H6. You divide this by 3, you divide this by 3. The 3 cancel, this one becomes 2. So it is still CH2. So even though it's a different molecule, it still has the same empirical formula. If we go to the third one, butene, is C4H8. You divide here by 4, you divide here by 4. This becomes CH2, the same thing as you have here. So sometimes a series of molecules or compounds can have the same empirical formula, even though their molecular formulas are different. Don't cram these things. It's not necessary. Nobody would ask you to explain this, but for purposes of understanding, sometimes we go deeper than what will be asked in the exam. So just know that these things exist, but don't cram anything. Don't memorize these things. Now we go straight to answering questions. The most popular question as far as uh, uh, empirical formula, molecular formula are concerned is to give you questions by which in which they would give you what we call the percentage composition of each element in the molecule or the compound. So let's take this first example. It says that a certain organic compound contains 41.1% carbon, 6.6% hydrogen, and 53.3% oxygen by mass. Calculate the empirical formula. Again, your teacher may have a different way of doing it, but usually I prefer this format where you put it in the form of a table. It's easier to see things so that you don't make a mistake. Now, when you are giving something in percentages, because the percentage affects all of them, your carbon, your hydrogen, your oxygen are all in percentages, you can assume that you are using 100 grams of the sample or the substance. And in that case, if it is 100 grams of the substance, then 41.1 grams, exactly equal to this one, will become carbon. Then exactly this amount will become hydrogen. And then this amount will become oxygen. So before you solve it, just write something like that. In 100-gram sample, then you just copy these same things without the percentages like that. Okay? Then we come to this table. This is a table of elements. You have your carbon, your hydrogen, and oxygen. Then the masses, you indicate them. This is carbon. You write here 41.1. Your hydrogen is 6.6. Your oxygen is 53.3. Then you go to your periodic table and look for the relative atomic mass of each one of them. I wouldn't refer to any periodic table here. I know them offhand. So carbon is 12. According to the periodic table, it's 12 here. Uh, hydrogen is 1 and oxygen is 16. These values are not magical. Just get yourself a periodic table and look for the relative atomic masses. It will be given to you there. Then the next step is to calculate the number of moles. Number of moles we did previously is mass over molar mass. Remember, all these things are in mass. You can write your mass grams. This is grams, grams, grams. So the number of moles of carbon is going to be the mass 41.1 over the molar mass or the atomic mass in this case, like that. Hydrogen is going to be 6.6 divided by 1. And then your oxygen is 53.3 divided by 16. Okay. So you go to your calculator and let's do it. So 41.1 or comma 1 divided by 12, that gives you 3.45. Now, when it comes to these ones, try to write as many as possible, at least to 3 decimal places. Okay. So this one is 3.4. This is the answer here. The answer here is 3.425. At least 3 decimal places. It makes things easier for you wherever possible. 6.6 divided by 1 is 6.6. And then this one is 53.3 divided by 16. So that gives you, according to my calculator, is 3.33125. So it's okay. I said 3 decimal places, so 3.331 would get you close. Then the last thing you have to do with respect to this is to find the simplest ratio. So you look for the smallest value. If you look here, this is the largest value, followed by this, and this is the small value. So you're going to divide all of them by the smallest value. So with respect to this, we are going to have 3.425 divided by 3.331. Okay. Then the next one is 6.6 divided by 3.331. Then the last one is 3.331 divided by itself, 3.331. So obviously this one gives us 1. It's straightforward. Okay. Anything divided by itself is 1. Then in the other one, we have 6.6 divided by 3.331. Uh, excuse me. 6.6 divided by 3.331. This one gives us 1.98. And then this one is 3.425 divided by 3.331. And that gives us this one. So this is for this one. This is for that one. And then this one is 1.028. So we can say 1.03. Okay. So now, because if you remember Dalton's atomic theory, we say atoms are indivisible, so we cannot have fractions. We have to convert them to the nearest value. So your 1.03 is approximately 1. Then 1.98 is approximately 2. Okay. And then obviously this is 1. So your empirical formula is going to be, we go back, we have CHO. So we are going to write here CHO. This one is 1. We don't write it. The hydrogen here is 2. And then your oxygen is 1. We don't write it. So this is how you write the empirical formula. Okay. This is the basic. So this is your empirical formula. Now, this is the most basic form of questions that you can be asked. All other questions follow the same pattern with a little variation, as we are going to see. So we'll finish with the first one. This is called case 1 or example 1. This is what they normally ask. Most of the questions are in this format. But then you know that in exams, you can't expect the same thing throughout. So another way of asking it is as we have here. Now look at what I'm saying. So this example says that an unknown compound contains calcium, oxygen, and hydrogen only. The percentage composition of calcium and oxygen are 54% and 43.2% respectively. Now, when you use this word respectively, what that means is that the first one corresponds to carbon, and then the second one corresponds to what? Oxygen. So you come and do the same thing here like we did before. You will say that in 100-gram sample, then your percentages are going to be the same. Your calcium is 54. Instead of 54%, you write 54 grams. Then your oxygen was given as 43.2%. So it's it becomes 42 grams here. Then the hydrogen was not given in the question, even though I have written it here, but I think I shouldn't have. So let's leave it like this and see how we are going to calculate it. Because there were three elements, calcium, oxygen, and hydrogen only, and everything you know in mathematics adds up to 100%. So if we know the two, we can calculate the other one. So how do we calculate hydrogen? The percentage hydrogen is going to be equal to 100% or 100 minus 54, that is for this one, plus 43.2. Okay? So when you do that, you will get it as what? 2.8%. Okay? So let's see whether when we add everything, we will get 100. So if you do that, you should get your 100. You're going to have 54. Okay, so let me do it here so that you see that it's not magic. This is 54 plus 43.2 plus 2.8. 2.8 here. When you add them, you should get 100. Okay, so that is how you get this one. So in terms of masses, you're going to write 54 grams here. Oxygen 43.2, and this one 2.8. The relative atomic mass of calcium, you can get it from the periodic table. This is 40. This one is 16. This is 1. So the number of moles is mass over molar mass, you remember, or relative atomic mass, depending on whether you are dealing with a compound or just an element or an atom in an element. So we are going to have this one. So here we are going to divide our mass here, 54 divided by 40. This one is going to be 43.2 divided by 16. And then this is going to be 2.8 divided by 1. Obviously, this one, anything divided by 1 is that thing. So here is 2.8. Then for this one, we go back, we use our calculator to calculate. We're going to have 43.2 divided by 1/6. And that gives us 2.7. This is 2.7. And then 54 divided by 40. That gives us, here is 1.35. Okay. Okay. So how do we calculate the simplest ratio? We identify the smallest value among them. This is the smallest. So we divide through by this number. So for this one, we're going to have 1.35 divided by 1.35. Then here we're going to have 2.7 divided by 1.35. And here we're going to have 2.8 divided by 1.35. So this is obviously 1 because anything divided by itself is 1. Then with respect to this, we use our calculators. 2.7 divided by 1.35. That gives us 2. So this one is 2. And then the last one is also 2 because it's very close. 2,8 divided by 1,35. Yeah, it's 2,07. So this is 2,07, which is basically 2. So if we round it off, we are going to have something like this. We are going to have our calcium 1. We don't write it. Our oxygen is 2. So this is our oxygen. This is our oxygen is 2. And then our hydrogen, I told you that atoms do not exist in fractions. So we have to round this off. We discard this one and then use this one. So this one, hydrogen 2. But if you look at this again, you see that we can improve it. It's not bad if you leave it like this, but it will show that you are amateur. In other words, you are not scientific enough. If you see this one and this one, they all have the same values. So you can put them in bracket and actually write them like this. H2. This is calcium hydroxide. Remember when I was teaching you how to write the formula of compounds? So yeah, you can leave it like this, but it's not nice. This is how it should be. We put it in the brackets. This 2 affects the hydrogen. So hydrogen is 2 and oxygen is also 2. So we are done with that. Then we move to the third example. The third example is similar to the other ones, except that there is a catch there. So let's see what we are going to do. This one says that an organic compound Q contains this, that of hydrogen. Okay, so it contains this of carbon, this of hydrogen, and this of oxygen. Determine the empirical formula. So we go straight and say that in a 100-gram sample, we are going to have 3,158, 31,58 grams of carbon, 5,26 grams of hydrogen, and 63,16 grams of oxygen. So this is actually mass here. So we are going to write here 31,58 grams. This one will write 5,26 grams. And then this one will write 63,16 grams. So it's similar to the previous one, but there's a small difference. We'll see what I'm talking about. Now, the relative atomic mass of carbon, you know it, is 12. That of hydrogen is 1, and oxygen is 16. I said you can get this from the periodic table. So we come to number of moles. The number of moles is mass divided by molar mass. So this is going to be the mass is 31,58 divided by, this case not molar mass, but atomic mass, because we are dealing with atoms. This one is going to be 5,26 divided by 1. And then this one is going to be 63,16 divided by 16. So we use our calculators to find what we are dealing with, we are going to get. So this is 31,58 divided by 12. And this one gives 2,632. Okay, it's the actual value is 2,6316667. So I just simplified like that. I said, for purposes of accuracy, always write it as close as possible to 3 decimal places. 3 decimal places outside this. It will be safer. Then with respect to this, obviously anything divided by 1 is that thing. So we don't have to waste our time to calculate. Then this one is 63,16 divided by 16. And we are going to have 3,9475. So let's say 948, something like that. So we inspect it and look for the smallest value. This is the smallest value. So we divide through by the smallest value. So this is 2,632 divided by itself, 2,632. Then we go to the next one. We are going to have 5,526 divided by 2,632. And then the last one is this 3,948 divided by 2,632. So this one obviously is going to give you 1. Anything divided by itself is 1. Then we check this one. 5,26 divided by 2,632. So this one gives us 1,998. So it's pretty close. Then let's look at this one. This is 3,948 divided by 2,632. And this one gives us 1,5. Okay. Now I gave you this question because I wanted to introduce this dilemma or this conundrum, something that is different so that you see how you calculate it. Now, in the past, we just simplify it to the nearest value, but this, even though 1,5 can be simplified to 2 in mathematics, in science, especially in chemistry, the value is too far away from 2. So to convert this directly to 2 wouldn't make sense. This can be converted to 2. So obviously, we would look at what is happening. This one here would be 1, because we got 1. This one, 1,99, yeah, it's approximately 2. But then this, we cannot say it is 3, because when you put it as 3, it introduces a big error. So we still leave it as 1,5. However, like I indicated, atoms do not exist as fractions. So in order to eliminate this 1,5, you have to multiply 2 by 2. So you are going to have 1 times 2, 2 times 2, and 1,5 times 2. So this one gives you 2, this one gives you 4, and this one gives you 3. So this is how you calculate this type of, or these types of questions. So this is also CHO, but then the value, your empirical formula is going to be like this. C2H4O3. So for this kind of questions, when you get a value 1,5, you should consider multiplying it by 2 to get it so that it doesn't create a lot of errors. Okay. So this brings us to the end of the various questions that they ask. Now we are going to look at another calculation, but this time you are calculating molecular formula if you are given empirical formula. Remember when I started, I gave you this example. I said, if you're given 2a plus 4b, and they say simplify this, you divide through by 2 and 2. Then this one cancels that, then this one you have 2. So your answer becomes a plus 2b, okay? So whereas this can be seen as the molecular formula, if we simplify it, we get this, and then this becomes like the empirical formula. Okay, so let's come to this. So on the basis of this, we can write something like this, that empirical formula, EF, times a certain value N must be equal to the molecular formula. Some people put dots there, but it doesn't really matter, okay? And therefore, we can also say that another way of simplifying it is by saying that the value N, this value N is equal to the molecular formula divided by the empirical formula. So either you use this or that, you will get what I'm talking about. Okay? So like in the case of this one, if we know the value of n as 2, all you have to do is to multiply your empirical formula by 2. So this by 2 gives you 4, this by 2 gives you 2. So it becomes 2a, 4b, like we have here. So that factor n is what you multiply through with respect to the empirical formula in order to get the molecular formula. So let's answer this question. Now, most of the questions that come uh, usually it is this particular one where you would calculate empirical formula, and from empirical formula, you go to molecular formula. So let me give you this example. It says that nicotine is an addictive substance found in cigarettes or in cigarettes. Analysis of cigarettes show that they contain 74% carbon, 8.7% hydrogen, and 17.3 nitrogen. So you have one, two, three substances. So excuse me. So, with respect to the first one, it says determine the empirical formula of nicotine. Show your calculations. So this is similar to what we have done previously. And so there is nothing new about this one. You say that in a 100-gram sample, 74 grams is carbon. Or 74, here is 74%. So this is 74 grams. This one is 8.7%. So this is 8.7 grams. And then 17.3 is also like that. So we just substitute it like that. This one, and that one. Then we go to the relative atomic mass, which you already know. This one is 12. This one is, excuse me, this one is 1, and this is 14. Okay, you can get it from any periodic table at the back of the periodic table. I mean, but at the back of every past paper, especially the standard ones, they have to give you a periodic table, and you will find these atomic masses indicated there. Okay, so we calculate the number of moles will be mass over molar mass. This is going to be 74 divided by 12. This is going to be 8.7 divided by 1. And this is going to be 14. No, not 14. It's going to be 17.3 divided by 14. So in terms of this one, your 74 divided by 12 gives you, this one is 6. This is 6 comma, according to my calculator. Let me clean this so that I write it well. This is 6 comma 1, 6.7. This one is obviously 8.7. And the last one is 17.3 divided by 1 for 14. And that gives you, this gives you 1.2357. So I'll just make it 6. So if you look through this one is the smallest value. So we divide through by the smallest value. This is 1.236 divided by 1.236. Okay. This is 8.7 divided by 1.236. And then this is 6.167 divided by 1.236. So when we do that, we are going to have 6.167 divided by 1.236. 236. And then here the answer is 4,989. Then this one is 8,7 divided by 1,236. This one gives us 7. Okay. 0.038. 039, it doesn't really matter. 039, and then the last one gives us 1. So with respect to this, if you look at this carefully, you see that 4,989, you can easily round it off to 5 because it's very close. Okay. This one will round it off to 7, and this one be 1. Okay. So the empirical formula will be C5, H7, and N1. We don't write 1 there. Everybody knows this is that. Okay. So the next question says that, so this is the first part of the question that we are dealing with. This is similar to the previous one. However, this is where the difference comes. It says that if the molar mass of the compound is this, determine the molecular formula. Okay. So what you do is you first have to calculate the molar mass of this one. So the molar mass of your C5, H7, N1 is going to be what? 12 times 7. I mean 12 times 5, not 12 times 7. 12 times 5. Okay? Carbon is 12 and there are 5 of them. So 12 times 5 plus hydrogen is 1 and there are 7 of them, plus nitrogen is 14 and there is only 1 of them. Okay. So with respect to this one, this is 12 times 5. This one gives us 60. 5 times 12 is 60 plus 7 plus 14. So plus 7 plus 14. And this one gives us 81 grams. Okay, this gives us 81 grams. Now, you remember that here they say if the molar mass of the compound is this, 1,6. So this is how you are going to do it. Oh, no. This is how you are going to do it. You are going to say something to the effect that the value N, okay, your value N is equal to your molecular formula divided by what? Your empirical formula. The molar mass is 1,6. This one, according to the question, is 162. You can see it here, 162. So we come here and we write 162. 162 divided by 162 divided by this one, empirical formula is 81. So when you divide this, you get 2. And therefore, we can say that our empirical formula, okay, times N should be equal to our molecular formula. So our empirical formula was previously C5, H7, and N. So we are going to write it like this. Going to write like this. C5, H7, and N. But there are 2 here. The N is 2. This is, oh, by the way, this is nitrogen. This is just a small letter N. It can be X, it can be anything. So we are going to say times 2. this value 2 here comes here, and whatever you get becomes your molecular formula. So it means that we must multiply through by 2. So 2 times 5 is 10. So this becomes C, 10. 2 times 7 is 14. So H, 14. And 2 times N is 2. So we are going to have that. So this becomes the molecular formula. I wish we could calculate another one, but I don't think it's necessary. You have to go through the most important thing is that the first one is like all the previous ones that we did until you get to the molecular formula. Then this is the only new thing that is being introduced, this side. So this is the part that you really have to learn from this side going down. So that is the only new thing. Okay. So that is it. Just revise and then you see it. Okay, so we are done with molecular formula and all those stories. Now we are going to talk about concentration. Now, the word concentration in chemistry simply means the number of moles of a substance dissolved in 1 decimeter cube of solution. Okay. Now, when you say something is concentrated, there are two ways of looking at it. A concentrated substance could mean you have a lot of the substance, okay, in a given volume of solution, or you can have few of the substance, but the volume decreases. You still have the same thing. You would learn this when you get to grade 11 and grade 12, especially in grade 12 when you talk about rate of reaction. But I'm just drawing your attention to it. When you say something is concentrated, it means that you have a lot of that particular thing in a small volume or in a small space. So let me give you an example. If you're someone who likes drinking Oros, I like Oros a lot. So I'm going to use Oros as an example. If you buy Oros, you can't just put it in water and start drinking because it is too sweet. So we say it is concentrated. So on the label, they will tell you to dilute it. It means that you add water to it. So the Oros as it is, the type you buy from the shop, we say it is concentrated. It means it has a lot of stuff. Whatever is inside is a lot. So you have to add water to it to dilute it. Okay, so this is important. Now, the formula for concentration is number of moles divided by volume, but the volume must be in decimeter cube or liters. Okay, decimeter cube or liters. However, some of the questions that would come across very soon, you will realize that they give you the values in centimeters cube. So to change centimeters cube to decimeter cube, you have to divide your centimeters cube by 1,000 and then you substitute it in. So let's answer a few questions like we normally do. These ones are pretty straightforward. It doesn't take long to get this. So question 1 says that 3 moles of hydrochloric acid or hydrogen chloride were dissolved in 2 decimeter cube of solution. Calculate the concentration of the solution. So you simply write concentration is equal to number of moles over volume. The number of moles here is 3. Yeah, your volume is that. So this is your number of moles here is 3. Your volume is 2. And that is what? 1,5. The unit is mole per dm cube. You can write it like this, or you can say 1,5 mole dash dm3. So this is how you do it. Okay. Number of moles divided by volume. Fortunately, the volume is in decimeter cube, so you don't change it. You just plug it in. So that is that. Then the second example is 0,5 0,5 mole of sodium hydroxide was dissolved in 250 centimeters cube of solution. Calculate the concentration. So again, you use your formula. Concentration is number of moles over volume. However, so your number of moles is this. There's no problem about it. Is 0,5. Okay. Your volume is not in decimeter cube. It's in centimeters cube. So I said to change centimeters cube to decimeter cube, you have to divide it by 1,000. So your volume is going to be 250 divided by 1,000, and that gives you 0.25. Okay? So your volume now becomes 0.25. And then your concentration becomes 2. 0.5 divided by 0.25. Excuse me. 0.5 divided by 0.25. That gives you exactly 2. So you're going to have 2 mole dm³ minus 3. Or if you don't want to write it like this, you can write it as 2 mole per dm³. So these are the two ways of doing that. So that is concentration for you. Then the third one is in mass. They say you are given this question here. And the question says 20 grams of sodium hydroxide was dissolved in 250 grams of water. Calculate the concentration of sodium hydroxide. Concentration is equal to number of moles over volume. But this is mass. It is not number of moles. So we have to change this to number of moles. And then the volume is not in decimeter cube. We have to also change it. So to change mass to number of moles, you go back to what we did previously. We said number of moles is equal to mass over molar mass. Okay? Or perhaps let me put it this way so that it's more scientific, that you don't get confused about. So it's a number of moles of N or sodium hydroxide is equal to the mass of sodium hydroxide divided by the molar mass of sodium hydroxide. Okay? The mass here is 20. If you did do the molar mass of sodium hydroxide, for those of you who have forgotten how to calculate molar mass, let me just do it again. The molar mass of sodium hydroxide is equal to the atomic mass of sodium, which is 23. You can get it from the periodic table, times 1, because there's only one of them here, plus oxygen is 16 times 1, and then hydrogen is 1 times 1. So this is 23 plus 16 plus 1. And this gives us 40 gram per mole, okay? 40. So to calculate the number of moles, you are going to say the number of moles of sodium hydroxide is going to be equal to this 20 grams that was stated in the question. The question, remember, it says 20 grams of sodium hydroxide. So that 20 grams is what you write here over 40, and that gives you 0.5 mole. So that is your 0.5 mole. We have that, but that is not the end of the story. Then we go back to our volume. Our volume is 250 centimeters cube. So we change it to decimeter cube. So your volume in decimeter cube is going to be equal to 250 centimeter cube divided by 1,000 centimeter cube. So when you cancel them, you are going to have 0.25 decimeter cube. So now you plug them in and say the concentration of sodium hydroxide is going to be 0.5 divided by 0.225. And like the previous one, we'll get 2 mole per dm³. Okay? So this brings us to the end of concentration. Now we're introducing the last piece of what we are going to do, and that is percentage yield. Now, to understand percentage yield, we need to understand some terms. The first one is theoretical yield. Theoretical yield is the maximum amount of product that can be formed from a chemical reaction when all reactants are completely used up. However, in a reaction sometimes some of the reactants would not react. Nothing is 100% in life, okay? So whatever you get is called the actual yield, not theory now. We're talking about actual. The actual yield is the true amount of the product that is formed in the reaction when the reaction is carried out in the laboratory. So your percentage yield is equal to actual yield divided by theoretical yield times 100. Now, your values can be in moles or mass. Okay, don't worry us. So if it is in mass, use your masses. If it is in moles, use your moles. As long as they are all in the same unit, moles, moles, mass, mass, it's okay. So this is the last question we are going to answer. It says that hydrogen reacts with excess oxygen to produce water. This is the reaction. Now calculate the maximum amount of water formed from this. Okay. Now, when you look at this one, we use mole ratio. The mole ratio here with respect to the coefficient here is 2 and 2. And therefore, the number of moles of water produced is the same thing as the number of moles of hydrogen. So there's no need to do any calculation. This is solution. So the number of moles of hydrogen is the same thing as the number of moles of water because it's 2 is to 2. The coefficients are the same. So therefore, the number of moles of water is also 1,5. 1,5 mole. Okay? So the calculation is not like the previous ones where you have to do proper calculation. Then we go to the last part, which says that if only 0.95 mole of water is formed, calculate the percentage yield. So this is the actual yield, okay, actual yield. So you say percentage yield is equal to actual yield divided by theoretical yield times 100. So this is your actual yield here. This is your actual yield here. I'm getting flu, which is 0.95. Yes, this is the actual yield. This is 0.95 divided by the theoretical yield. So what we got here, 1.5 times 100. And so 0.95 divided by 1.5 times 100. And that is going to give you 63.33%. So this brings us to the end of this topic. Hopefully continue another time, but I think this is all that you need to know with respect to 10.3 according to the ATP. So I would encourage you to just go back and answer a number of past papers. But before I stop, let me just give you a certain hint. Sometimes they can give you a question where they give you the percentage yield. Let's say the percentage yield, the theoretical yield, and ask you to calculate the actual yield. So that is still mathematics. It's not something that you should worry about. So if they give you a percentage yield and then a theoretical yield and say calculate the actual yield, all you have to do is to put your percentage yield here and then your actual yield here times 100, and then you solve for x. It is mathematics now. It's no longer physical science. Okay. So this brings us to the end of today's lesson.